So before we go on to work out what we can use these antiderivatives for, we need to highlight a little problem and its solution. Here are three functions: x squared plus 1, x squared plus 2, and x squared plus 3. And if we carry out a derivation on them, we find the derivative. In all cases, we come back to the value 2x. In other words, we've lost some information about the original function. So if we now decide we want to apply the antiderivative operation to this, we get x squared, but what we don't get is any of these particular constants here on that side. So we need to compensate for the information that has been lost when we carried out the derivative function here, and then when we took that back to where it came from. So what we do is we add c. C represents the lost information on this side. In the end, it's not going to worry us too much because we don't need to use some of the integrations that require you to work out the value of c. We're going to see that that c is going to disappear. So this c here has got a special name. Okay, it's called the constant of integration. Now, this is called an introduction to integration, and this is the constant of integration. It comes out of the fact that we apply an operation which gives us an antiderivative. The two parts are linked together. The antiderivative is a function which is output, and the integration is what we're actually going to learn how to use the antiderivatives to do. These antiderivatives allow us to find areas underneath functions. Let's see that happen. I take a nice simple function, y equals x squared, y equals x, sorry. A function of x equals x, and for each input value of x we get the same output value of y. And we can ask ourselves the question, what is the area of, say, that triangle there, or the area of the bigger triangle there as well? We could even ask ourselves, what is the area of this four-sided shape here? We can use antiderivatives to find out what that area is. But before we do, we can also use a simple piece of geometry from primary school. How do you find the area of a triangle? Let's imagine that we have a triangle and it has a length of x. Under the function f of x, then this is also going to be x. What we've got then for a triangle is the length of the base multiplied by the height divided by 2. That's how we work out the area of a triangle. Now in this case, the base is x, the height is x, so the area under that particular function is x squared. And clearly the area increases or decreases as we increase or decrease the value of x. What about the process of anti-deriving something? Let's take this function and find an antiderivative for that function and see what we learn. So we have a function in x, okay, is equal to x to the 1. Let's apply our little technique for finding an antiderivative. We increase the power and we decrease by the new power. And we divide by the new power, sorry. We increase the power and we divide by the new power. And when we do that, we increase the power to 2 and we divide by the new power. And there, very quickly, you should see the connection here between the antiderivative and the area underneath a function as x changes. That is an extraordinary, powerful piece of mathematics. And what we're going to learn how to do is apply that to the general case of any particular function. Clearly, with a linear function, it's easy to see what is happening. Most functions that are useful are non-linear, but that doesn't stop this antiderivative technique from providing us with the area under the curve.